Today we'll learn the extraction of copper from chalcopyrite, that is CuFeS2. So firstly, we carry out the roasting of CuFeS2, which gives us cuprous sulfide, ferrous sulfide and sulfur dioxide. Now these two sulfides individually react with oxygen to form cuprous oxide and ferrous oxide. Now we should note here that Fe is more reactive than copper. Ideally, the Cu2O which is formed here could have been directly reduced into copper by using coke as the reducing agent. However, what happens here is that the FeO which is formed here, it does not allow the direct accumulation of Cu2O in the reaction mixture. Rather, what it does is that the FeS reacts with Cu2O here to form FeO and Cu2S. So here we can see that in this reaction, the concentration of Cu2O in the reaction mixture is decreasing as it is being converted into Cu2S. And this problem is further worsened by the fact that this FeO which is formed here reacts with the sulfide ions present in the reaction mixture to form FeS. Now this FeS again reacts with the cuprous oxide present in the reaction mixture to form Cu2S. So now this is a cyclic process which is hindering the formation of cuprous oxide. Without this problem, the direct obtaining of copper from cuprous oxide would have been way easier. So now the main problem here is FeS. We need to do something about it. See, FeS is not allowing formation of cuprous oxide. So we have to remove it. So how will we remove it? By addition of silica flux. Silica, which stands for SiO2, reacts with the FeO forming FeSiO3, which is obtained in the form of slag. However, what about the FeS present in the mixture? It has not yet reacted with O2, and for its fast removal from the mixture, we need to react it with O2 so that it can be reacted then with silica to form FeSiO3. Now, once the slag is removed from the reaction mixture, we now have Cu2S with us. Now, Cu2S is reacted with O2 to form cuprous oxide along with sulfur dioxide. Now, cuprous oxide is reacted with the Cu2S present in the reaction mixture to form copper along with liberation of sulfur dioxide gas. Now, another problem that arises here is that some of the sulfur dioxide hasn't completely been liberated from the furnace. The trapped SO2 leaves behind blisters in the copper which is formed here. So now this is another problem which needs to be tackled, and this is done by the process of electrolysis. In electrolysis, we place this blister copper at the anode. At the cathode, we place pure copper, while in the electrolyte, we use CuSO4 solution. So here you can see the setup of the electrolytic cell. This is the electrolyte, that is CuSO4 solution. This is the anode in which blister copper is placed, and at the cathode pure copper is present. So what happens here is that the copper which is present in this blister copper first needs to be oxidized into Cu plus. The main idea is that the copper which is present here needs to be moved to the cathode. Now we will carry out this movement by first liberating the copper trapped in this into Cu plus ions, so that these ions can swim through the electrolyte, reach the cathode, obtain an electron from the cathode and get reduced back into copper. Now this copper will again get deposited into on the cathode. So here is the electrolytic process that helps us to convert blister copper into pure copper. So now if we see the reactions that are taking place here, anode, this is the impure copper which is oxidized into Cu plus, giving an electron. Now this electron flows through the circuit and reaches here, and this Cu plus ion which has migrated to the cathode again accepts this electron, gets reduced into Cu and gets deposited on the cathode. Hence, we are finally able to obtain 99.99% pure copper.